Hello and welcome to the AP ECE Chapter 16 Precipitation Equilibrium Problem Set. Let's take a look at problem number 3. In problem number 3, you were asked to write equilibrium equations given KSP expressions. So you're given this column of information here on the left and asked to come up with the equilibrium expressions here on the right. If mercury 1 and chloride ions are in the KSP expression, with the chloride ions being squared, you can safely assume you're dealing with mercury 1 chloride, which is Hg2 2+ to combine with 2 Cl ions. To get an equilibrium expression, you take the solid substance that's insoluble and you break it apart into the separate pieces, noting the appropriate numbers of them in coefficients in the equilibrium equation showing up as superscripts in the equilibrium expression. You follow along for the following ones in the same fashion. Let's take a look at D, for example. In this one, you have a 2 as the superscript for aluminum and aluminum's ion, and a 3 as a superscript for the sulfide ion. So you know you're dealing with aluminum sulfide, Al2S3. Take a look at problem 5. In problem 5, you're given the KSP and one equilibrium concentration, then you're asked to calculate the other ion's equilibrium concentration. So in part A, you've got cadmium hydroxide, and you can write an equilibrium equation for it. That's right here. And you can find the KSP value. You're given that KSP value 2.4 times 10 to the negative 14th, and you're given that the cadmium concentration is 1.5 times 10 to the negative 6 molar. So you write your KSP expression, taking into account the coefficients in the equilibrium equation, and then algebraically solve out for the hydroxide concentrations to one unknown here. In part B, similar problem, write your general equation. You've got a KSP value. Down here is your KSP expression, taking into account your coefficients within the equilibrium equation. Plug in your KSP value, plug in your known here, 2.4 times 10 to the negative 4th is the concentration of the arsenate, and then solve for your copper. In part C, you're dealing with zinc oxalate, breaking apart. You have a KSP value for it. You're given the oxalate ion concentration. You know your KSP, plug and chug. Solve out for your zinc concentration of 3.1 times 10 to the negative 6th molar. Let's take a look at problem 13. In problem 13, you're told that well water has 3 milligrams of calcium 2+ ions per liter, and if 0.50 milligrams of sodium sulfate is added without altering the volume, will it precipitate form? And then the question is, what should the sulfate ion concentration be to just start precipitation? So this is a problem where you kind of have to think about what you know, what you have, and how to proceed from there. So I would find what the concentration of the calcium is in this particular sample. You have 3 milligrams of calcium, and then you can convert into grams, then you convert into moles, and you use the fact that it's a per liter thing, and you can find your calcium ion concentration, 7.5 times 10 to the negative 5th molar. Then I would find the sulfide ion concentration, knowing that you have 0.5 milligrams of sodium sulfate. So run through your dimensional analysis, and you can find out that the specifically sulfate, just the sulfate out of it, not the sodium sulfate, just the sulfate, is 3.5 times 10 to the negative 6th. Then you calculate a Q value, which is sort of like, is this at equilibrium, past equilibrium, not yet to equilibrium? So you know your KSP, you can write an equation for this. It's always about equation writing. You put your calculation, your known numbers for calcium concentration and for sulfate concentration, and you find that you get a value of 2.6 times 10 to the negative 10th. Now that 2.6 times 10 to the negative 10th is lower than the 7.1 times 10 to the negative 5th, so Q is less than KSP, no precipitate will form. This corollary part of this question says, wait, how much sulfate would actually need to be there to make it precipitate? So you make the assumption that the calcium ions stay at the same concentration, 7.5 times 10 to the negative 5th, and then this actually is like the previous problem where we're just trying to find out one of the concentrations given the other concentration of an ion and the KSP value, and you find that it should be 0.95 molar of sulfate to make this thing precipitate.